Okay, welcome back. This is a short video about valid and invalid source connections. So let's say we have an independent source, which we model with a little circle, right? So this will be a voltage source. Let's say it's a 12 volt voltage source. So you could hook it up in what would be a valid connection here. You could go plus to plus and negative to negative. That would be okay. And why? Well, let's pick a point down here and call this 0 volts. So when we go through the source, we come out the other side, we're going to have more energy. We're going to have 12 volts. And the same thing's happening on this side. This wire across the bottom is all 0 volts. You could write 0 volts here too if you want. And then we're going through this connection and rising 12 volts. So we've got 12 volts all across the top, 12 volts all across the bottom. There's no voltage changing here through this wire. There's no difference in voltage, so the current will be 0. And these guys will be happy to put out their 12 volts, and everything's okay. Everybody's happy. But let's do an invalid one. Let's say we take our 12 volt source and we hook it up wrong. We go positive to negative and negative to positive, which, by the way, I've done. You could do it in some kinds of sources. It can be a really bad thing. It depends on the source. I've done this with jumping a car battery, and that's a really bad, very bad way to do this. Other sources, they'll have safeties inside, or maybe they won't be able to put out as much current. But a car battery is can put out pretty high current for a brief amount of time. It can melt stuff. You can weld with car batteries. There's people that do that. So what's wrong with this? So let's start here and go with 0 volts. So we're going to come out of this thing. We're going to have 12 volts. Let's bring the 12 volts across here. All right. And then we're going to go through this guy. We're going to come out here. We're going to have 24 volts. So, that makes this 24 volts, which means we're rising up 36 volts, which means bring the 36 over here, which means we're rising up 48 volts, which is bring this 48 over, so 72, and it's to infinity. Okay, and basically bad things are going to happen. You're going to get smoke and stuff like that. Okay, this is with ideal independent sources. This is a little bit unrealistic because there's no resistors in there. Let's think about, well, what would happen if you had a resistor in there? So let's add some resistors. So let's say you had this thing, 12 volts, and then you stick a resistor in here, R. So this is the so-called valid connection, the plus to plus and minus to minus, but I've added a resistor. So still there's no voltage potential. There's still 12 volts here and 12 volts here, and 0 volts here and 0 volts here. So there's no potential difference across the resistor, so I equals 0. You can put an arrow for the I direction, but there is no I. Because there's no potential difference, so there's no current I. So that this is still okay, still okay. What about if we do that with this invalid connection? What if we put a resistor in there? Because here we've demonstrated that with no resistance, this voltage is going to go to infinity, and things are going to explode. But what if we add a resistor in there, which is more realistic? In most cases, there's at least a little bit of resistance. Jumper cable for a car, that's a big fat cable. It has a very low resistance. It's more similar to this first case than it is to what I'm drawing down here. But let's think about it. So let me give this a reasonable value, 120 ohms. That's not a super whole lot of resistance, but it's not a trivial resistance. So So the current in our circuits classes, we always imagine the current coming out of the positive terminal. So the current's going to come out this way. All right. So there's going to be a voltage drop across this resistor, and let's call that V sub R, and it'll have a polarity like this. That is, the polarity of the voltage drop in a resistor it's always opposing the current, because it takes, well, it's just always opposing the current. And so we could solve, so if this is 12 volts and this is 12 volts, we could write a KVL equation for this circuit. So let's just draw a loop around this way, call this loop 1, and so we'll write KVL 1, indicating this KVL is generated from this loop right here. So we'll go around, and so if we're coming in the positive terminal, we write a positive term. So V sub R is positive, okay, and then we're coming in the negative terminal here, so it's minus 12, and then we're coming in the negative terminal here, so it's minus 12 again. Those sum to 0, that's KVL. So we can get the voltage drop across the resistor straight away. It's 24 volts, which it has to be. I mean, the 12 volt sources have to balance the load. All the voltages have to balance. That's what KVL says. So there's 24 volts total source, and then all of that voltage is being dropped across the resistor here. So there you go. And we could keep going, and we could do Ohm's law at the resistor. You could write Ohm's law sub R or something like that. So so Ohm's law is V equals IR. So let's solve it for I. I is V over R. So we found out, or we just figured out that V sub R was 24 volts. That is, the voltage dropped across the resistor is 24 volts, and the resistance in the resistance itself is 120. So this is 0.2 amps. Okay, so that's a pretty low current. You could play with these values and see what you get. If you had a lower resistance, then you're going to get a higher current, and if you have a higher resistance, you're going to get a lower current. So a wire has a very, very low resistance, so it's going to be extremely high current, and things might explode. So anyway, this is just a simple example of hooking up valid and invalid. The book just talks about this right here, these two cases, and it doesn't actually put a resistor. But keep in mind, in real life, there's a resistor. We could even go a little bit further, really. Let's go ahead and do that. So let's think about a real world. Like, what about a real world car battery? One of these things, like what looks like that. It has these little doohickeys on top, plus, minus, Duracell, or something. One of those car batteries, right? 12 volts. Okay. Let's build a model of that hooked up correctly and incorrectly, and just think about the model. I mean, we're trying to build models of real world circuits, so let's try and do that a little bit. Let's do this correct jumper. So say you have a dead battery, and you call the cops out to jump your battery. They'll do that for you. Well, the campus cops will. So let's do a couple things. Let's draw the battery with this little battery symbol right here. Let's say you have a dead battery on this side and a good battery on this side. So the dead battery is going to be 2 volts, let's say, because the voltage in a battery varies. That's how you indicate its health, is by looking at the voltage. So there's also an internal resistance in the battery, not the wires. Although there's an internal resistance in the jumper cables, that's true, but there's also an internal resistance in the battery. So we can model that, right? So this is the internal resistance of the battery, the resistance inside the battery, and the voltage in the battery. So And then on the good battery, let's say it has the same internal resistance, 0.03 ohms, but let's say it's a good, healthy, charged up battery, and let's say it has 12 volts. Okay, so this is the correct way to jump a car, right? You have a dead battery with a low voltage in it and a good battery with a high voltage, and you go plus to minus, or rather plus to plus and minus to minus. And what's the current? Well, which way is the current going to go? Well, it's going to go from the good battery to the bad battery. It's going to go from the higher voltage, the 12 volt side, to the low voltage side. So it's going to go this way. So there's I, and we can write a KVL. So let's write a KVL going this way. Let's call this loop 1, and we're writing the KVL in the direction of the I. That's a good idea. So KVL 1, the voltage in, so let's call this something. We got to call this VB1, and we'll call this VB2. The voltage drop across the internal resistance. So VB1 plus VB2 minus 12 plus 2 equals 0. That's just the KVL going around here. So let me put some of the polarities in here. So I is going this way. So the drop due to the internal resistance is going to counteract that current. That's the way they go. And in this guy, it's going to running out of room here. But the voltage drop across the resistor over here is going to be this way, because it's, once again, the current's going around that way. So the resistance will sort of fight that current with this polarity drop. The simple rule, the plus sign is always on the resistor. The plus sign is always where the current's coming in. Okay, so that's how I got this equation here. So I'm just going around this way, and I'm coming in the plus sign, so this term's plus. I'm coming in the plus sign, so this term's plus. I'm coming in the minus sign, so this term's minus. Coming in the plus sign, so this term's plus. Those sum to 0. So the voltage due to the battery resistance total, that's just VB1 plus VB2. It's going to be 10 volts, and we can solve for I now. I is it's the voltage battery resistance total over the resistance total. So it's going to be 10 volts over 0.06. So it's going to be 166 amps. Okay, which should seem, reasonable if you've ever jumped a car battery. That's a reasonable amount that's going to go over that way. And what else did I do? I kind of looped these together, and I just solved for the total I. These are the same resistance, so they'll have half the voltages. So this 10 volts here will be split across here. There'll be 5 and 5 there, 5 volts here and 5 volts there. And what else can we say? That's about mostly what we can say. So this is a correct connection where we hooked the cables from the plus side of the battery to the plus side of the battery. And the internal resistance here is, the signs are different, but that's a little bit more of a complexity you have to deal with. This is inside this battery, these VB1s and VB2s. The internal resistance, it's in here really. And then we've hooked this up to another battery. Okay, and then the external terminals are plus and minus, and that's what we've hooked up here. So physically we've done this. We've gone minus to minus, plus to plus, but inside there's a resistance in both of these, and they have polarities that are resisting the current direction, just depending on the voltage. So it gets the modeling gets a little more complicated. That's part of why I wanted to do this. Okay, I'll leave it up to you guys to maybe solve this if you're interested in for the case of a incorrect connection. What if somebody went plus to minus and plus to minus. And we could draw this out and see what would happen. Okay, what else can we do? Since we're talking about modeling in general, right? So we started off with just a simple valid connection, invalid connection, and it's easy enough to solve these problems. That's what the homework's like. I just want you to be aware that in real life there's almost always some kind of resistance, and that does affect things a little bit. So even this invalid connection, if you add a resistance, which you really would have in real life, it's going to change things a little bit. But once again, if the resistance is very small, which it would be for a wire, then it's closer to this ideal case, this ideal invalid connection, things like that. And you could take the model a little bit further and do this, and we come up with this 166 amps. Let's just talk about batteries, a little bit more. So 166 amps, that's a reasonable value, and this is a 12-volt battery when it's freshly charged, and this is a 2-volt battery. When you first hook it up, 166 amps will flow. That's what will happen, because we have a 10-volt potential really pushing this current across. Now, what's weird about batteries is that this voltage here will rise pretty quickly. Okay, and this potential will become closer and closer to zero, so the current will drop way down. Okay, so you know what? I guess I could draw a graph. Like, what is I versus time? It's going to be, start out at 166 amps, and it'll drop pretty quickly. Okay, and maybe down to something like 15 amps or something like that. So most battery chargers, they're in this range. The battery charger, they're kind of down in this range, and the voltage will do the same thing. Like the voltage will rise on the V on the dead battery. Like it starts out at 2 volts. Oh, I should have put that here. Let me put that down here because it's going to go up. 2 volts. It's going to go up pretty quick, like that. But so there's that. What about the energy? Well, the voltage is going to rise pretty quickly, but that doesn't mean that this thing is charged. Okay, the voltage is not the exact same thing as energy. So that's another thing to think about. And let's just think about that a little bit. So let's just think about lead acid car batteries. So lead acid, like just all kinds of battery chemistries, right? There's lithium ion, nickel cadmium, alkaline batteries, all kinds, sulfur batteries, all kinds. So there's lead acid batteries that are the standard ancient technology that's been around forever for cars. Even those vary. So there's let's consider a starter battery. This is the kind of battery in most cars that has to turn the starter motor, right? And let's consider a deep cycle battery, which you might have in, like, for a small solar setup, or like in a boat to run the lights and things, like in an RV or something like that. So a starter battery has a volt. Let's look at the volt amp curve. It might be something like this. It might start out at like 12.4 when the battery is like super healthy, and when you start putting out current, the voltage will drop, but it'll do pretty good up to say 600 amps, and then the voltage will just cave. It doesn't want to do anymore. They're designed to put out enough current to turn a starter motor, right? So I'm basically drawing the current and the voltage and the current relationship for a starter, the kind of battery that has to turn a starter motor. What about a deep cycle battery? They're kind of they don't have such good starting current. Like it might be 12.4 volts when the battery's super healthy. When you start drawing current, it'll do pretty good, but then it'll, like, you know, it might start dropping off at maybe something like 300 amps, or maybe even less. So a starter battery puts out high amperage at a reasonable voltage, and deep cycle batteries less so. This is another, just a characteristic of batteries, but we're talking about modeling really in more general terms. But why would you want to use this deep cycle battery? Because they have more energy. It's like the starter battery, you could think of it as maybe having more voltage, you know, or I don't know how to say it. Voltage and current relationship is good. Then the deep cycle battery not so much, but the deep cycle battery might have more energy in it. You could represent that with the amps and hours. So let's put time over here. Let's say in hours, because they talk about amp hours for batteries. So, but it's really just time. Let's look at both of these two batteries, a deep cycle and so here I'm talking about VI in this column, and here I'm talking about energy in this column. So starter battery energy, well, let's just pick an amp rate, say 20 amps. It might only be able to supply 20 amps for, say, 12 hours or so, and then it conks out. Whereas a deep cycle battery might be able to put out 20 amps for, you know, something like that. So this is still time in hours. Okay, so just to summarize, a starter battery might have the ability to put out a high amount of current at a reasonable voltage, whereas a deep cycle battery doesn't. But the advantage of a deep cycle battery is it can put out a lower amperage for a long amount of time. So really this corresponds to energy. The area under the curve, the amp hours in a battery, it's not exactly energy because you still need to multiply times voltage, but this is proportional to the energy. Okay, so so I took what was a pretty simple concept for your homework, this idea of valid connections and invalid connections, and then I just want to expand on that a little bit because we're talking about modeling. Really, the broader picture is just modeling. You can start to put in resistors, and you can start to think about you know, the voltage differences in a real-world connection and solve for things, and then you can start to, you know, this idea of the current and the voltages in batteries, you know, might lead you to start thinking about the energy characteristics. All right, that's it.